the electrophilic addition to an unsymmetrical conjugated diene. So if we're going to do a addition to a diene like this example one that is unsymmetrical, the first thing that we need to do is we need to look at these two alkenes and determine which one of those two alkenes is going to be the most reactive alkene. And so the reactivity of an alkene in an electrophilic addition reaction depends on how stable the carbocation is, because the carbocation is that high energy intermediate that we need to form. So the more stable that carbocation is, the lower the activation energy barrier for the reaction. And so in order to determine which of these two alkenes is the most reactive, we need to look at the carbocations that we form. So if we first examine this end alkene and we protonate the alkene, giving us the allylic cation, and this allylic cation is tertiary, and then we draw the resonance form of that, and we see that after we shift the pi bond, we have a primary allylic cation. So remember with resonance forms that the true structure is somewhere as an average of these two. So an average of the tertiary allylic and the primary allylic. And then we want to compare the stability of that carbocation system to if we had protonated the other alkene. So if we protonate on the other end, we again form an allylic cation. So you're always going to form an allylic cation from a conjugated diene. So when we do that, the first cation that we get is a secondary allylic carbocation. And then to find out the overall energy, we also want to look at the resonance form. So we move this pi bond in, and that gives us a primary allylic cation. And so on average, this first cation is the more stable, which means that that end alkene is our more reactive alkene. And so if we want to look at the product, we're going to look at the reaction of this end alkene. And so we're going to look at this under low temperature conditions, which is kinetic conditions, and then we will look at high temperature conditions, which is thermodynamic conditions. So at low temperature, first of all. So low temperature is kinetic. And we know that the kinetic product will always be the 1,2 addition product. So in this sense, because we've got a handy rule to follow, the kinetic product is an easy one to come up with, provided you can identify that most reactive alkene. And we've already done that. So I'm going to go ahead and draw the diene starting material. We will draw the HCl. And so when we protonate, we will get the carbocation that we saw on the top of the slide. So our initial carbocation will be this tertiary carbocation. We added the hydrogen to the 1 position. The position next door is 2. That's where this 1,2 addition comes from. So if the chloride ion simply attacks this carbocation, then we will have the 1,2 addition product. So this is the kinetic product for this reaction. If we want to determine the thermodynamic product, so this is at a high temperature. We don't have a rule here for the pathway. It does not matter what the pathway is that forms this product. It matters that you form the most stable product. And since our product is an alkene, we are evaluating the stability of the alkene. So we are looking for the most stable alkene. And so we've already drawn a mechanism here, and we've already got to one possible product. So what I'm going to do is draw the mechanism to show the other possible product that could form. And so we will still have the same first protonation step, where that more reactive alkene attacks the hydrochloric acid. there is the initially formed carbocation. So if the chloride attacks this, we will get the product that we saw above, that 1,2 addition product. If we draw instead the resonance structure, and this allows us to see where else we have an electrophilic carbon in this intermediate. So when we draw this, we've moved the pi bond in, and that has put the positive charge on the end of the chain. And so if the chloride ion, instead of attacking here, attacks the end carbon instead, then we get a different product. So we'll have the chloride ion attacking that carbocation. And here is the product that we have formed. And so we need to look at these two products and say which one of those is the most stable alkene. And so if we look at this first alkene, it is mono-substituted. If we look at the second alkene, it's di-substituted. And so that second alkene is the most stable alkene. And so under thermodynamic conditions, this will be the major product. So this is the thermodynamic product. And let's add the temperatures in here. So low temperature is always a kinetic product, no matter what reaction you're talking about. How low that temperature is depends on the reaction. We might well see reactions where 200 degrees Celsius is considered a low temperature. This is not one of them. What you will see most often in your textbook for this reaction is a low temperature of around -80 degrees Celsius and a higher temperature that's actually not all that warm, and it's at +40 degrees Celsius.